The question tells us that there is an inspector, Inspector Clouseau. He has arrived at a murder scene where there is a butler and a maid. There is also a knife. Okay, before we proceed, let's define some random variables so we can solve the problem being asked for. First, let's have B denote the butler, and we can say B can take two values, either murderer or not murderer. Similarly, we can call the maid M, and this can also take two values, murderer or not murderer. For the weapon itself, knife, let's call it K, and this time it can take the values used and not used. We also have some prior information before we actually do anything with this problem. We are told that both the butler and the maid cannot be the murderer, so the probability of this joint probability is 0. We are also told that the probability of the butler being not the murderer, whilst the maid is the murderer, is 0.04. The probability of the butler being the murderer and the maid not the murderer is 0.64. And the probability that neither are murderer, as in some other third party has come in and killed the victim, is 0.32. Not in the question itself, but in the original example, we were also told some extra information about the knife use. We are told that the probability that the knife is used, given neither the butler or the maid are the murderer, is 0.3. The probability that the knife is used, given that the butler is not the murderer, but the maid is the murderer, is 0.2. It's 0.6 given that the butler is the murderer and the maid's not the murderer. And finally, if both of them are the murderer, which in our case is impossible, the probability of the knife being used is 0.1. Okay, for the question itself, we are asked, if we know that the knife is used, perhaps they've found the blood on the knife of the victim and it's a perfect match, so we have 100% knowledge the knife is used, what is the probability that the butler is the murderer? Okay, let's try tackling this. The first thing we can do is demarginalize the first variable, B, using the variable M. So as a quick reminder of what I mean by demarginalize, is if we have a single variable, probability of x, we can write it as a summation of joint probabilities with respect to another variable, y in this case, which iterates over all instances it can take. So why don't we do the same thing but with M? So the maid can take two values, either not murderer or murderer, and we've included these two joint probabilities. But we do know from the left-hand side that the probability of being both a murderer for the butler and for the maid as a joint probability is 0. So we can quickly say we can take this bit out, and we are left with only this. So our original question has boiled down to being, what's the probability of the butler being the murderer and the maid being not murderer, given we know the knife is used? We can do a bit of simple Bayes rule. So if you recall, Bayes rule is a way of swapping around the given probabilities we have. So probability of A given B is equal to probability of B given A times the probability of A, all divided by the probability of B. This is pretty simple to prove from the rule of given probability, as in the original definition. So let's apply Bayes rule, and we get this more complicated looking expression. If you notice, we actually know every term in the numerator, but it is the denominator which we are less sure about. So why don't we perform our favorite trick and demarginalize the denominator? But in this case, we can demarginalize using both variables b and m, because we know we have a lot of information where the knife used with respect to both b and m is already given in our prior knowledge. So doing that, we get this expression. Recall that the summation has to go over every value of the butler and the maid that they can take. So in the summation there will be 4 terms, because both the butler and the maid can take 2 terms each, murderer or not murderer. Now we can simply sub in the values and we get these numbers. All these numbers have come from the left hand side because this was our prior knowledge. And if you pump this into your calculator, you'll get an answer of 0.787, which is around 78.7%. The question is actually not quite done yet. It also asks us to modify the demo script, demo Clouseau, given in the BRML toolbox to account for the modifications in the question relative to the original example given in the textbook, example 1.3. So, before we dive in, as a quick reminder, if you don't have the BRML toolbox in your MATLAB, you can get it quite easily. I've made an introductory video showing how to, and that has been linked. So do go get the BRML toolbox and do have a go at implementing the modifications. So, I don't want to modify this original script itself, so I'm going to copy everything, Control A, Control C, and place it in my own script. I shall call it my demo Clouseau. We actually want to keep most things the same because the modifications are just to do with the specific distribution values. So the variable names are the same, Butler, maid, and knife. The values these names can take, variables can take, are still the same. Murderer and not murderer for the butler, similarly for the maid, and finally for the knife it can take the value of used or not used. What is different is this expression. What they've said here is that the joint distribution of butler, maid, and knife can be written as the probability of the maid times the probability of the butler times the probability of the knife given the butler and the maid. This is not true in general. This would only be true if the butler and maid were independent variables. But this is clearly not true for us. We know, for example, if the maid is the murderer, then the butler cannot be the murderer for definite, because we are told that the probability of both the butler and the maid being the murderer is 0. That is an impossible situation. So to account for that, we will use a given probability here. So the probability of the butler given the maid. So this expression is a general decomposition using the law of total probability of a joint probability of 3 variables. This applies to any number of variables in joint probability where you can decompose it into given probabilities in this manner. For us, we now have to define the actual values in each potential. So what we mean by potential is each one of these separate product terms in this like series of products or probabilities. So the general idea is we've been able to split this joint probability into many products, each of which we call a potential, because we can independently define the potential without referring to any other potentials. So let's go define the potentials. The first one is the Butler potential here. This has previously been defined for the potential of the butler on its own, but now we also have this given maid, so we have to account for this variable in our conditional probability distribution now, the probability of the butler given the maid. The first thing we can say is let's consider the situation both the butler and the maid are murderers. So the probability of the butler being a murderer given that the maid is a murderer. Let's get rid of this line because we no longer need it. This we know for definite is 0. We know that if the maid is a murderer, the probability of the butler being the murderer is 0. Now let's consider the case that the butler is not the murderer, but the maid is the murderer. Probability of butler dot table murderer. Sorry, not murderer. Let's consider that first. Murderer, and the maid is the murderer. This we can say is 1. There's 2 ways of going about it. One, we can say that it's 1 minus the value above, 1 minus 0, because that's how probabilities work. Or we can say intuitively that if the maid is the murderer, and we know that they both cannot be the murderer, then the probability that the butler is not murderer is 100%. Okay, now let's consider the other two cases. I'm just going to copy this so I don't keep typing the same things again and again. We're now going to consider the case the butler is the murderer and the maid is not murderer. I.e., we want to know the value of the given probability that the butler is a murderer given the maid is not murderer. For this we can use Bayes' rule, so we can say that this is equal to the probability of the butler being a murderer and the maid being not murderer, which is 0.64 if you recall. I'll write that down here. Divided by the probability of the maid being not murderer. So the maid is not murderer in two cases, either when the butler is murderer or when the butler is not murderer. So if you remember from the prior knowledge, that is either the case of 0.64 plus the case of 0.32. 0.64 being the same as the numerator, and the 0.32 case being the situation where neither the maid or the butler are murderers. This value should come out to be 2/3 if you put that into your calculator, or you can see that in your head if you just divide through by 0.32 the numerator and the denominator. But now let's consider the final situation where neither are murderers. So this is the probability of the butler being not murderer given that the maid is not murderer. This is simply going to be 1 minus the value above because probability is sum to 1, as the given bit is the exact same in both cases here, not murderer. And we have iterated through the two different values butler can take. Or we can use the given probability rule as above and say this is the probability of the maid and butler being not murderer, which is 0.32, divided by the probability that the maid is not murderer, which is exactly the same as above, 0.64 plus 0.32. Now we've only got one more thing to change, and that's the potential of the maid. Luckily, the maid still is independent of anything else, or at least the potential is, in this decomposition of the joint probability distribution. So all we have to define is the probability of the maid being the murderer. 0.2 is no longer correct because that was for the example 1.3. The probability of the maid being the murderer is either they're both murderers, which is 0, plus the probability that the maid is a murderer and the butler is not murderer, which we have been told in the prior knowledge is 0.04. So the answer is 0.04 here. Then the probability of the maid being not murderer is obviously going to be 1 minus 0.04. Or, if you remember, it's 0.64 plus 0.32, which both give 0.96. And that are all the modifications we have to make. Alright, we can check if our modifications have been correct. Do you remember we don't actually have to modify the knife conditional probability distribution, the probability of knife given butler and maid, because all these values are still true in our prior knowledge, the 0.3, the 0.2, the 0.6 and the 0.1. Okay, so to verify that the answer we had got earlier, which was 0.787, being the probability of the butler being the murderer given that the knife is used, we can verify that by running this program. So first thing we need to do is save this. I'm going to save this as my demo Clouseau. And now I'm going to run it. I simply type my demo, I can just tab that to complete, demo Clouseau, and run. And voila! It's given us the probability of the butler being the murderer, given that knife equals used, is 7.868852 times 10 to the minus 1, which is 0.787 approximately, exactly as we had predicted. Well, so our calculations mathematically in this slide were correct, and that has been verified by our modifications to the MATLAB program. You may also now observe that the maid and butler have a direct connection, so the butler is dependent on the maid, given by the probability of the butler given the maid, and the knife is dependent on both the butler and the maid, given the probability distribution is probability of knife given butler and maid. And that was our decomposition of the joint probability of knife, butler, and maid. And that is that.